Yeah, thanks so much for the introduction to Wilbert. And thank you all so much for being here. Thank you to Monica and Dennis for agreeing to give us a talk about your research. Just as a little reminder, ARAPIC is the Interagency Arctic Research Policy Committee, and it brings together leaders from many different agencies, departments, and offices across the US federal government to enhance the collaboration on research in the Arctic. And ARAPIC Collaborations is the public branch of ARAPIC, and it aims to facilitate the interagency communication, coordination, and collaboration to advance Arctic science. And the Modelers Community of Practice, which is this group here, aims to enhance the understanding of the integrated Arctic system through the use of regional and global Earth system models. And while modeling is an incredibly useful tool, we all know that it also involves substantial uncertainties from many different sources, and particular in the high latitude regions where data are often sparse and unique processes play an important role in system dynamics. So quantifying and where possible mitigating these uncertainties as much as possible is always a priority when modeling. And we have a wide range of methods that are being used to address them. And one of such methods is ensemble modeling, which I think we're all familiar with, and it offers a significant opportunity, but it also presents some potential pitfalls. And so in this session, we're going to hear from two scientists who will discuss their approaches to handling model uncertainty in general and ensemble modeling in particular. Monica Morrison, who we'll hear from first, is an interdisciplinary researcher at the National Center for Atmospheric Research in the Climate and Global Dynamics Laboratory. And she's been working on designing scenarios of combined climate interventions for applications for Earth system models to better understand the efficacy and safety of these responses to the climate crisis. And today we'll hear from her about representational fitness and traditional uncertainty quantification in Earth system modeling. Afterwards, we will hear from Denis Felikson, who is a research physical scientist at NASA Goddard Space Flight Center, and he works on combining observations and models of the Earth's ice sheets to understand the processes that drive the change and also to improve projections of sea level rise. And he will be telling us about the Cryosphere Model Comparison Tool, or CMC, which is a community tool for evaluating ice sheet models. Thank you so much for being here, and with that, take it away, Monica.
Okay, great. Thank you. So let me go ahead, share my screen and get going. Okay, play from start. And just to check quickly, it's still not presenter view, it's audience view. Perfect. Okay. So as Hannah noted, I'm currently at NSF's NCAR in Boulder, Colorado, and I work as a project specialist, program specialist, actually. I always mix that up, sorry. My background is in philosophy of science and ethics. And what I'm going to do here today is to kind of talk about some of the philosophical analyses that can complement our traditional ways of trying to assess uncertainty in our Earth system models, to try and kind of get at the way in which there's certain qualitative features of models that matter just as much as being able to quantify uncertainty in order to determine if they're appropriate for use and to understand the sort of information that they can give us for our various sorts of regional or actionable studies. Um, Okay. So, this is to just kind of give you something to think about as I go into the rest of my talk. Um, thinking about uncertainty in Earth system modeling. And I want to begin here because I think that this highlights both, as I noted, the quantitative nature of models and assessing uncertainty, but also the qualitative nature of models and their components, which is largely what this talk is going to focus on, thinking about what's known as representational fitness, as well as traditional uncertainty in climate models. So let's imagine that there's two Earth system models that produce nearly identical historical sea ice trends, and they fall well within observational uncertainty. They both make the ensemble cut, not being extreme outliers, kind of being middle of the pack. Model A represents sea ice thermodynamics through explicit brine pocket dynamics, while Model B uses a bulk salinity approach. Model A includes melt pond evolution explicitly, and Model B parameterizes it. And when we use both models to project forward, we see that even though they were in historical agreement for the most part, they actually diverge dramatically in what they're telling us about the future. So if we were to do a traditional multi-model ensemble, the question is, does the ensemble capture the uncertainty in relation to the various ways in which these processes are being explicitly represented or parameterized? Or do we just sample parameter values within similar or different, what we might call representational frameworks? And I ask this question because it's these representational components of models that might not be fully assessed with traditional tools for quantifying uncertainty. And so that's what I want to really focus on here. So before talking about how we go about quantifying uncertainty, and I'm sure if you've worked with ESMs, this is something you're all familiar with, I'm going to quickly just delve into where it emerges from. So first we have one source, which is known as parametric uncertainty. And this is uncertainty that's epistemic, so related to our knowledge of the world as opposed to aleatoric, which is due to just the nature of the system. But parametric uncertainty is that we don't know the exact values for parameters in our equations. So from an atmospheric perspective, we see this a lot with respect to uncertainty around microphysics, so cloud droplet nucleation rates. There's also uncertainty around things like soil carbon decomposition constraints, etc. Another source of uncertainty is scenario uncertainty. So we develop these scenarios to try and look at what future emissions will look like, what future land use, land cover change might look like, population growth. We use those in order to develop forcings for our models, but we don't know what the future is actually going to look like. So there's a lot of uncertainty going into how we go about describing those possible futures that then we force the models with in order to get our future projections. There's initial condition uncertainty. So not only do we have imperfect knowledge of the current state of the system when we initiate our runs, but we also are dealing with a chaotic system. And so these chaotic dynamics mean that even from the same starting point, it might evolve differently. And this is the internal variability within the chaotic system. So these two uncertainties are initial condition uncertainty. And then we also have what's known as structural uncertainty. And so this again is a form of what's known as epistemic uncertainty. It's due to incomplete knowledge of the world that we're trying to represent. And this is uncertainty about the mathematical structure of our models. And this includes uncertainty around which processes to include, how to go about representing them, at what resolution that should be done, et cetera, et cetera. And what's interesting is that model developers encounter structural parametric uncertainty. And this is, again, uncertainty around how we have incomplete knowledge of the world or the target system that we're seeking to describe with our models. And in response to that, they're kind of forced into a situation where they have to make what are known as representational decisions. So when choosing what to represent and how to represent various things in the system, they question whether to represent it explicitly, whether we parameterize it, at what level of detail do we need to represent it, what amount or degree of idealization, simplification, or obscuration is permitted. And these choices are often in response to an incomplete understanding of the underlying physics of the system. So an example is that we're deeply uncertain about cloud aerosol interactions and how to go about representing those in the atmospheric components of our models. Different modeling centers respond to the uncertainty with different representational strategies. Some will have detailed microphysics schemes where they have a lot of assumptions embedded in those representations. Others have what are called bulk approaches, and still others just use statistical or stochastical parameterizations to represent, right, these complex interactions. But each choice made by a different modeling center reflects a judgment about how to deal with this epistemic uncertainty or the incomplete process understanding. And so modelers are responding to uncertainty, and in their response to uncertainty, actually introducing uncertainty as well. And so one thing I want to point out is that when we then think about model structure, it's not something that's given to us by nature. It's actually something that's constructed by developers through the decisions that are made in order for them to grapple with the uncertainty they have about the system when they're going about trying to describe it in the modeling effort. And these decisions shape everything downstream. Now, we do have traditional responses to uncertainty. We've developed these sophisticated tools and methods for quantifying various sources of uncertainty, right? So we can use perturbed physics ensembles, PPEs. These explore parametric uncertainty by varying parameter values within a single model structure. They tell us something to the effect of, given this specific way of representing clouds or representing the carbon cycle, how uncertain are we about the parameter values that we've chosen? We have multi-model ensembles. So these are MMEs, and they sample structural uncertainty by comparing models from different institutions or that have different development trajectories. The CMIP archive, as you probably know, is a traditional example of this. There's a multitude of different models from different modeling centers that have different kind of representational trajectories embedded within them, given that different modeling centers are making different representational decisions. There's also initial condition large ensembles. So these are large ensembles, many, many members in the ensemble, done with a single model, and they allow us to better quantify internal variability in the system, which arises from chaotic, irreducible uncertainty of the system, as well as epistemic uncertainty that we have about what the exact initial conditions to start our model from are. And together, along with scenario uncertainty, which I didn't put in there, these give us the classic Hawkins and Sutton, it's a 2009 paper, view of uncertainty in ESMs. So they give us the total projection uncertainty characterized in terms of these various sources. And what's really interesting about Hawkins and Sutton is they actually looked at, depending on your projection, what sort of uncertainty has the most bearing on the projection. And so initial condition uncertainty is actually something that comes up, as well as parametric uncertainty and structural uncertainty in like decadal to 50 years out, where scenario uncertainty is actually the dominant form of uncertainty the further you get towards 2100. And I didn't say scenario uncertainty in here. One way that we try to get a handle on scenario uncertainty is to have a variety of different scenarios across a span of possible futures. And these various sources of these various scenarios allow us to kind of sample, right, different potential end of 2100 warming scenarios to kind of see like what that span might be or that envelope might look like. Okay. So, what I want to point out now is that all three of these ensemble approaches share a common assumption. And this is why I want to focus on what's known as representational fitness and also thinking about qualitatively assessing, right, representational fitness uncertainty, if you will. All of these sample uncertainty within a space of representational choices that modeling centers have actually made. And as I pointed out earlier, structural choices emerge from epistemic uncertainty. We have representational choices, what we want to do with our cloud aerosol scheme, that are made in response to uncertainty experienced during the development, right, of our model. And when we assess uncertainty that might be introduced by those in a quantitative sense, we're doing so in the space of those decisions that have actually been made. And for example, with respect to sea ice models, we can have those that explicitly resolve flow scale dynamics versus those that treat sea ice as a continuum. And the point here is that when we look at those actual decisions, right, we don't just look at these being different parameter values or different quantitative structural choices in a model. We see that they're not just parametrically different. They actually embody different responses to that first order epistemic uncertainty about what processes and scales matter, right, to represent in a specific way in our model. And so each of those represents something qualitatively different in a model as well, mainly different modeling teams' judgments about things like which process details we can afford to ignore, what's computationally tractable, so there's pragmatic constraints here, what observational constraints we can trust, and what aspects of the system we care most about given our purposes. And so this representational gap is that there's more than just these quantitative, right, things that we can actually look into in our models and how they represent the world. There's qualitative things that we need to attend to as well that these traditional methods for exploring uncertainty don't really get at. And so this is why, and this is the big thing I work on right now, we need to think about the representational fitness of a model because that's key to getting at these qualitative things that are going on in the model that will also help us understand what you might just consider some sort of qualitative uncertainty that emerges from the assumptions and these other sorts of choices that we make in the course of development. And representational fitness is just to say that, right, models aren't good or bad based on where they might perform with respect to the multi-model ensemble, middle of the pack versus an outlier. They're fit or not fit for a certain purpose. So a model that's fit for projecting September sea ice extent might be inadequate for projecting sea ice thickness distribution. And that comes down to thinking about the decisions that were made, those qualitative features of the model, as well as the uncertainty that we can explicitly quantify using various sorts of ensemble methods. So the philosophical point is when we build a perturbed parameter ensemble, we're exploring uncertainty that's conditional on one representational response to first order uncertainty we have about the system. And when we build a multi-model ensemble, we're sampling from those representational responses that happen to get made by well-resourced modeling centers. And those things that we're sampling from, which are qualitative in nature, are just as important as that sampling strategy. So why do representational decisions matter? Just to kind of hit it home a little more. Well, ensemble STRED might underestimate uncertainty if all models carry similar or the same representational choices in response to that first order uncertainty we have about the system. Representational decisions affect how we interpret model agreement. So robust projections might reflect, and that's where we get kind of a grouping or agreement across models. They might reflect genuine physical constraints that we're getting right in our modeling strategies, or it could just be their shared representational strategies amongst those models that are showing agreement. And actually, there's been work done by Reto Canuti, and then I think Bode is maybe the other one out of Germany who wrote about this a couple of years ago, but they actually find that models that have this similar genealogical developments, so they share various components or parameterizations, or they emerged from similar and shared modeling efforts, do actually show more agreement than models that were developed under different institutional conditions or that don't have shared components. Most important, though, I want to point out is that representational decisions, if we look at them and we try and understand this qualitative nature of models, change what model selection should look like. We don't just want to choose models based on historical performance or where they might be within a multi-model ensemble, because they might favor particular representational approaches. So what we need to really do is ask if, given the way that these features of the system I care about are representative, are they adequate or fit for an application? And one of the other reasons why historical performance or agreement with observation might not be sufficient, but is a necessary condition to choosing a model for one's purposes, is that they've actually shown in many different cases where contemporary climate models show agreement with observation because of underlying compensating errors, and the physical representation of processes is actually wrong. And so that's another reason it's important to get at these qualitative things. Um, and here's maybe a specific example, and Hannah knows this one because I give it in all my talks because I find it fascinating. But why it's really important to look at these qualitative things. So there was a study done in 2021 by Briley et al. Out of University of Michigan. They did a qualitative assessment of models to try and cull an ensemble to determine which ones had basic representation of large lakes, because they wanted to have a culled ensemble or an ensemble of models that were best suited for regional projections of the Laurentian Great Lakes. And if you're quantifying uncertainty in a traditional manner to determine what the bounds look like for these models, right, and trying to just pick a spread, you're going to overlook some of these things. But what this figure is showing is that they wanted to see, okay, if we think that having representation of basic land, lake, atmosphere is necessary for being admitted as part of our ensemble, which models can we choose? The ones in green have three-dimensional representation of lakes. The ones in orange have some sort of weird representational decisions that they made to have, like an ocean grid cell, or they have some sort of three-dimensional or one-dimensional model that it's not clear it can actually represent those things, or maybe even it was difficult to determine what was being represented in the model. But the one that's really interesting is these ones in red. They found that in some cases they didn't even represent lakes. And so if you're just doing kind of, looking at ensemble spread, you're looking at these various sorts of components of models, focusing on quantitative attributes of models or of your multi-model ensemble, choosing from looking at these sorts of features, you're going to miss the fact that some of the models that you might be choosing don't even represent what are the fundamental physical elements of the system that drive the climate, the regional climate that you're interested in. So I'm going to end in one moment because I think I'm already over time. But what can users of climate models do? And really, it's move beyond just accepting ensemble spread as our uncertainty estimate and actually look at these kind of qualitative, right, things that are introduced based on our ways of trying to get around uncertainty when we're developing models. So really considering model fitness for purpose in a qualitative sense. So before selecting a model, explicitly identifying what processes and variables are critical for your application. If you're projecting permafrost thaw, you probably need specific carbon cycle and thermal representations. Ecosystem dynamics or transitions, phenology and disturbance will matter more than, right, looking at the ensemble spread for something like global temperature. Investigate representational choices. So model documentation is not perfect, but we're getting better at it. And it's not just technical specs of the model. I studied model documentation, wrote my doctoral thesis on looking at understanding what different modeling centers were doing by interrogating that model documentation. And you can actually have revealed in that different design choices and why they were made. So why different processes are explicitly resolved versus parameterized, why they choose to simplify or ideal certain things at the expense of the model not being able to do X, but they put their effort into the model being able to do Y instead. And then again, look beyond the ensemble mean. So models that agree might share representational assumptions. So really understanding kind of that ensemble agreement, understanding that ensemble spread, might not just looking at quantitatively what that looks like, but also looking at what the qualitative features of the models are that might be promoting that spread that you're seeing. And most importantly, match the model to the purpose. When you're choosing the best model or the best modules in order to have a cold or targeted ensemble, you should always be asking what models are best for what purposes. And then some of this does require having a little bit of a shift in our modeling practices. And so I think the email told me to have a provocative question to end on. And so this is my provocative question. How do we actually build a culture in climate research where we have greater transparency around model representational choices? Because it's subpar, if I'm being honest. We don't talk about that a lot. So this qualitative assessments are actually difficult. And how do we make fitness for purpose just as important as kind of our routines for calculating things like ensemble spread, parametric uncertainty, etc. Okay, thank you for your time.
Yeah, thanks so much for the super interesting talk, Monica. I'm going to ask you all to keep the controversial question in mind for later when we'll have a more general discussion, and I think we'll hold questions to the end and move over to Dennis's talk.
All right, can you all hear me? Great, great. And I'll share my screen. Okay. Let me know if you can't see or hear. So my name is Denis Felikson. Thanks for the invitation. I'm very happy to be here today. I'm a research scientist at NASA's Goddard Space Flight Center. I put my full intro there in the chat. Um, Today, I'll give a short talk that's half research results and half an advertisement for the Cryosphere Model Comparison Tool, or CMCT. This is a tool that has been in the works for quite a while. It was led by Sophie Nowicki when she was at NASA's Goddard Space Flight Center. She's now at University at Buffalo and continues to be involved in this, as well as a whole host of other people that have contributed. The goal is really to create a community tool for evaluating models that the community can contribute to and work on. So every time I give this talk, I have to add names to this list, which is a great thing. The motivation behind this, well, I'll give the ice sheet motivation, but we're trying to expand this tool into not just ice sheets, but also global glacier models, but I'll get to that at the end. So I'll give the ice sheet motivation. So I'm sure, as many of you all know, ice sheets are a large source of uncertainty in sea level projections. So this is a figure showing global mean sea level on the left, and then two sea level projections from AR6 at two locations, New York City and in Ghana. At 2050, that's the top row, and 2100. And so the Greenland ice sheet and the Antarctic ice sheets are shown in orange and purple. I won't go into the full details of this figure, but suffice to say that ice sheets are a very large source of uncertainty. And so one way to narrow that uncertainty is to use observational constraints on those models, and that's sort of the motivation behind this CMCT tool. So I'll show you some results from so first the research part of the talk. So I'll show you some results that show you why we need this tool and kind of some different answers that we get when we constrain model ensembles with different observational constraints. So first I'll show you a model of just the Northwest Greenland sector of the Greenland ice sheet. This slide is kind of an eye chart. It has all of the details about the model setup, but this is a configuration that I set up in ISSM that was initialized in 2007 and it's run to 2100. And then I designed the ensemble using 150 samples using Latin hypercube and sample several ice sheet model parameters that I won't get into the details on, but this is a 150 member perturbed parameter ensemble from one model, ISSM. If we look at the mass change of the Northwest sector here, remember this is just Northwest Greenland, this is what the time series looks like. So again, it was initialized in 2007, runs to 2100. The red lines here show the mass change from Northwest Greenland in units of millimeters of sea level equivalent over that time span. You can see the spread in the ensemble. And in blue, I've also plotted the IMB mass change for this sector of the ice sheet. And then what I've also done is colored the red lines according to how well they match the observations. Okay, so the darker red indicate a better match with observations over 2007 to 2020. And this is what the probability distributions look like in 2100. Again, this is in units of millimeter sea level equivalent. So in blue is the prior distribution showing the full ensemble spread where each ensemble member is weighted equally. And in red is a posterior or calibrated distribution where I've calibrated using the IMB mass change. And so you see we get a narrower spread, and although our peak, our median is probably at about the same value. Okay, now let's get under the hood a little bit here to dig in a little bit. So here I'm showing one example of an ensemble member that performs well when you compare it with this particular observation type. So here is the highest weighted ensemble member when we compare with this observation of regional mass change from IMB. On the left is the observed mass change. This is gridded mass change, I believe. Um, and then in the middle is what the model shows. So it, pretty noisy, but the kind of the broad patterns look okay, let's say, although, and on the right is the residual between the two. We still see some outlet glaciers that don't behave quite right. But overall, the pattern looks okay. Below is a bad ensemble member. So this is now. Oh, by the way, I know I'm not supposed to use good and bad according to Monica's talk, but so I'll change that for the next talk. But here's the not fit for purpose model. So this is the lowest weighted ensemble member, and you can see that it has way too much mass loss, and so the residuals, the modeled mass change doesn't look anything like the observed mass change. So this model gets deweighted. Now, here's the ugly part of this here's one ensemble member that was weighted highly in this ensemble because it reproduces the observed regional mass change pretty well. But when we look at the spatial patterns, they are totally wrong. Now, something crazy happened in this configuration. I actually don't even remember what. Any modeler or any ice sheet scientist could take a look, one quick look at this model output and say, obviously this is wrong. So, but this is just kind of an illustrative example to show that while regional mass change is a good metric, we need other metrics, especially for these high resolution model configurations like what ISSM is able to do in order to provide better, stronger constraints on sea level change projections, ice sheet mass change projections. However, other metrics, other observational metrics, don't always give consistent answers. So here's some other work that myself and collaborators have done where we this is a different model ensemble that was simulating Greenland's committed contribution to sea level change. And what we did was we looked at three different observation types: velocity change, uh, thickness change. This actually is surface elevation change, but we just called it thickness change in the paper to simplify, just assuming that the bed is stationary over time. And then basin scale mass change, just like we had used before. And when you use these three different observation types as constraints on the model ensemble, you get these three different probability distributions shown in green, orange, and black. So while the velocity and mass change posterior probability distributions look similar, something is a little bit off when you use thickness change, and we sort of hypothesized in the paper what that could be. But the bottom line is that as a community, as an ice sheet modeling community, we're still exploring which observational metrics are the most meaningful for model evaluation. And so, therefore, we argue that we currently, as a community, need an easy to use, extensible, and standardized framework for modelers to be able to experiment with different observation types in an easy way. And so here comes the pitch for the cryosphere model comparison tool, the CMCT. What the CMCT is it provides two things. One are what I call, quote, cleaned observational data sets, and then code that can be used to compare, to evaluate model output against those observational data sets. And the reason this is important is that for many satellite observational data sets, there's always some sort of pre-processing or cleaning that must be done before it, to remove outliers and things like that, to reproject sometimes the observations into the model space that need to be done, that can be done in a consistent way so that every modeling group can use them off the shelf instead of having to do that themselves. And so that's the goal of the CMCT. So the idea is that the CMCT provides a suite of observational data sets. Here are the ones that we currently have configured to work with the code. We have the IMBY mass change time series. We have mass change from gravimetry, and we have surface elevation change from altimetry. The way that the CMCT works is it requires that the model output that is provided is CF compliant with variables and conventions as defined by ISMIP. So these were set up by the Ice Sheet Model Intercomparison Project for CMIP 6 or ISMIP 6, and ISMIP 7 is adopting the same conventions. And so all that we require is that the model output conform to those conventions, and then the code knows exactly how to interpret and use that model output. What we've done recently is try to modernize the software. So we have now created a CMCT Python package and Jupyter notebooks that serve as examples for how to run the code and the underlying Python modules that are within the Python package. And so then what this code does is does the comparison in a standardized way. It takes the model output and brings it into observation space typically, and then outputs residuals in the form of figures, netcdf files, and in some cases CSV files, like for the IMBY mass change time series, you can get CSV files as output. Another sort of modernization thing that we're continuing to work on is to allow the CMCT to support different use cases. So the idea behind this is that in some cases, the model output will be very large in terms of just data volume compared to the observations. In other cases, the model output will not be that large, and a modeler may want to upload a model to where the observations already are housed. And so we're trying to support all of those use cases. So, for example, if you have one simulation and you want to do a quick comparison against observations, we have installed CMCT as a tool on the GHub platform. So if you go to the ghub.org, this is a platform that is led by University of Buffalo, and they have a whole suite of a growing collection of tools that can be used there through basically a GUI interface. So you can just point and click, upload your model, run the tool, and download the output right away. So this is the case where you don't have a huge model ensemble. You maybe have one or several simulations. You can just upload them to GHub and run the tool quite easily without having to install the CMCT at all. In other cases, you may want to run the CMCT on a common computing platform. So here I'll put in a plug for the Cryo Cloud. So if you go to cryointhecloud.com, you can read all about this project. Some of you may know about it already. This is a NASA-supported project that provides a Jupyter Hub on AWS, on Amazon Web Services computing platform. And the nice thing here is that what you can do is you can take the CMCT Python package that we've created and the environment, install on the Cryo Cloud and get going there. What we've tried to do is use configure the CMCT to use the correct Python packages that are already provided on Cryo Cloud. So I think this is true. You shouldn't have to do any extra package kind of configuration, although if you do, it's in our environment. But the drawback here is that you have to not only do you have to upload your model or ensemble of models to the cloud, but you also have to download the observational data sets from different places. Our documentation on the CMCT helps explain how to do all of that. But the advantage that you gain here is that you can run the CMCT on this Jupyter Hub that they offer in the cloud, and all users can access that simultaneously. And access the configuration that you've set up. So this could be a nice way of having your group all working on the tool at the same time, or doing the analysis at the same time. Finally, there may be cases where you have a huge model ensemble. It's housed somewhere in a local system, like your local HPC, and you really don't want to have to move that around. In that case, you can install the CMCT Python package again on your local system, and then download those data sets to your local computer and run them there. So this is kind of just the philosophy behind the CMCT software, that we want to be able to support all of these use cases. We are continuing to expand the CMCT. I had some summer students last year who worked with me to work on adding observational data sets like Greenland ice sheet extent from a paper by Chad Green and others that came out a couple of years ago. Ice sheet velocity change is something that we would like to add to the CMCT as well. And dynamic ice sheet mass change. So right now we have just surface elevation observations, but we'd like to be able to account for SMB and firn compaction and provide observed dynamic ice sheet mass change, which would be a more kind of direct constraint on a lot of ice sheet models. And then finally, as I said in the beginning of my talk, we really want to embrace the cryosphere part of the cryosphere model comparison tool. So beyond evaluation of ice sheet models, we're starting to add functionality to be able to evaluate global glacier models. This is also work that a summer student did last summer to add some notebooks that can evaluate global glacier model output against observations, and this is just a plot from one of her notebooks that she configured to do that. So I don't have a provocative question at the end of my talk, but I do have a call to action. If you remember, the whole idea here, as I said in the beginning, was to make a community-based tool that's open source, easy to use, but also extensible by the community. And so I encourage you all to try it out for yourself. This QR code will take you to our GitHub repository. I can also drop a link in the chat. Um, Try it out. Let us know if it's easy or difficult to use and configure. Open a GitHub issue on a repository to start a discussion about any additional observational metrics or features that you would like to see, maybe new sorts of plots or visualizations. And then finally, you or other members of your group can contribute to the code base. You can see our contribution guidelines. We try to follow typical open source practices. I will say that now that we've sort of modernized and brought things into Python and created a Python package and are working around Jupyter notebooks, this has been a very nice tool to develop summer student projects around because the tool works. There's sort of a foundation there, and then these summer students can add new functionality by bringing in a new observation data set or a new way to do the analysis, a new visualization. So this has been a really nice way to sort of formulate summer student projects for us as well. So I will end there. Yeah, I'll drop a link in the chat, and I'm happy to take any follow-up questions.
Thank you so much, Dennis. That was super interesting. It's exciting to have easy to use tools. I feel like that can be really hard with modeling. I'm excited to check out the repository. Yeah, I think we should move on to the question and discussion part of this meeting. So if anyone has a question, please either just unmute yourself or raise a hand or put it in the chat and I will read it out loud.
Hi, this is Hailong. I will go ahead and start the question. Yeah, thank both speakers for the fantastic talks. So I do have a question for Monica about those different categories of uncertainties. I wonder, uh, it's easy to understand to compare those uncertainty within the category. Uh, uh, do you have some thoughts to share how to gauge the uncertainties from the interactions between the different categories? For example, some parameter uncertainties might be bigger in different scenarios or with different same scheme might be different in different models. So do you have some thoughts to share how to compare the uncertainties from the different categories and how the uncertainties may interact or affect each other?
Yeah, actually, I'll point you to that 2009 paper by Hawkins and Sutton, and then the work that has been generated from that 2009 paper, because a lot of people have kind of taken the framework that Hawkins and Sutton adopted to try to look at, with respect to different questions, what are the relative contributions of different sources of uncertainty, with respect to using models for those questions, and how do they maybe compound one another. So just to give you an idea of Hawkins and Sutton, and I noted this in my talk, but one of the things that they found that if you're using climate models for decadal projection, it's the structural and the parametric uncertainty that is going to be really difficult, right, to gauge, where scenario uncertainty is going to be something that doesn't exert as much of an influence on those sorts of questions. However, if you're looking out to 2100, scenario uncertainty is what is going to dominate. And things like uncertainty from initial conditions or internal variability matters a lot less. And there was a paper a couple years ago by Bonin. Oh my gosh, and I'm forgetting Gordon Bonin's the second author. But they actually then kind of took that framework and instead of asking questions about time frame, they looked at with respect to various sorts of land-based questions about like vegetation dynamics or looking at various sorts of things about land use, land cover change, or ecosystem dynamics. What do relative contributions look like? Um, and so that kind of work kind of gets at that. I'm not sure that apart from, I'm not sure what work has been done to really try and look at the way in which on a very nuanced level, structural uncertainty and scenario uncertainty might interact with one another. Most of the work is to try and parse how different sources of uncertainty impact different sorts of model uses or applications. Um, yeah, so and I mean, if you just look at Hawkins and Sutton, I know people are now doing it for, like cloud aerosol interactions. Where's the largest source of uncertainty? What do relative contributions look like? Things like that. So that's probably the
Yeah,
best thing to
thank
look
you.
at. Yeah.
Very helpful. Thanks.
Yeah.
I have a question too. I think it's kind of for both of you. In the same vein of asking which uncertainties will dominate in the future, do we have so I thought it was really fascinating Dennis, to see which observational metrics are really meaningful now. Is there any approach to understand which ones might be meaningful in the future and how that can sort of tie into making the decisions on which structural elements maybe are more important to represent versus parameterize?
Ooh, this is a good question.
Yeah.
Especially, well, what it made me think about is the marine ice cliff instability process and sort of the controversy. Well, I shouldn't say controversy, the disagreement among the modeling community about the importance of that process. Yeah, so it's tricky because there are some processes some that may come into play, years from now that we haven't observed. That's just not in the observational data, or it's not constrained well enough by paleo data, for example. So very tricky, but I guess, yeah, this is something I was thinking about too during Monica, your talk, that this is where we sort of have to qualitatively think about what we're doing rather than blindly quantify things, right? So we have all of these great observations now, satellite-based records, but applying them blindly can lead down the wrong path. So I don't know if I have a great specific answer to your question, Hannah, but I think, yeah, being careful and thinking through qualitatively about what processes the different models are representing and how they're being represented is very important.
Yeah, well, obviously I agree with that. But I do think we have a lot of potential uncertainties with respect to observations that we need to tackle. Where if we had better observations, it would help us increase the fidelity of how we're representing various things in the system. And so it's kind of a question of, right, prioritization and how do we go about doing that. And I think actually one way to do that is to have modelers kind of maybe consult with communities about, look, if these are the things that you care about the model doing, what are the things that we need to represent? And then that can maybe be used to better inform targeted observational campaigns. I don't think that there's a lot of communication, unfortunately, that happens between different communities. And so, at least on the side of developers of ESMs, right, we're making judgments about what uncertainties we need to decrease, where we need to increase representational fidelity or include more processes based on our own assumptions about kind of what people might be using the model for, which oftentimes I found are not hitting the mark very well. Um, so it would help to just have a better idea of how to prioritize. And right, it, yeah, I would say it's would be easier to prioritize. And with respect to understanding maybe what observations are critical to be able to better constrain our models for future projections, I think again that's kind of based on a qualitative understanding of the system where we need to understand interactions and emergent properties, and how we can kind of better conceptually or causally map out the system and then identify what we can have observations for that would help us constrain those things that might shift under future warming scenarios, which we already have some sort of basic understanding of because of our theoretical knowledge of the system, if that makes sense. Um,
Yeah,
yeah,
thanks. It's probably the kind of question, if we had a final answer to it, we wouldn't be having this meeting.
yeah.
But yeah, Mike, do you want to ask your question from the chat?
Okay, if one goes back in time to the 80s and 90s and even 70s, the way one done perturbation experiments like going to 2 times CO2 or something, um, there were lots of systematic errors in the models that were known. And yet it was thought that by doing a perturbation experiment and comparing two different results, the difference might be more valid, might be reasonably valid, even though the actual simulation had errors in it or something like that, and ITZZ or a whole host of things.
Mhm.
I guess I'm wondering if a systematic evaluation has been done of that presumption. Did it make sense in the past to do that? Because now it seems what you're all doing is working to get the models to match observations very well,
Mhm.
and sort of not, I don't know if that means you're not tolerating systematic errors, but when you look at results. But I guess I'm just curious if there's been an evaluation of doing that, because all the early CO2 things and lots of other experiments back then were done with early models that had all sorts of flaws in them or limitations in them, and yet the results sort of have persisted over time on climate sensitivity and some of the other things.
Yeah. So with respect to looking at that kind of way of responding to perturbation experiments, I actually know nothing of whether or not they've looked at the validity of that approach. And with respect to, so when you say systematic errors, are you thinking of like the fact that CMIP6 models have like SST biases and they show like an El Nino like warming despite the fact that we see it trending in a different direction? Like in all the models for some reason sh show that? Is that what you're thinking?
Uh, Oops, I'm sorry. Yeah, I mean, most of the models would show some systematic errors. They had coarse resolution. They didn't have,
Yeah.
a lot of the orographic things. They didn't have the Great Lakes. They didn't have a bunch of other things. Um,
Yeah.
but there was a sense that some of the larger scale results that came out from the comparison of differences made sense. So we're headed into a time probably where there's going to be a bunch of thinking about climate intervention, looking
Mm-hmm.
to the future and how that works. And how accurate does one have to become? Does one have to get in all of this detail in order to have a sense of that might be possible and make sense, or will cause something? So I guess I mean, there's always going to be differences from observations. I guess I'm trying to understand if one still can get some, if there can be agreement that you can get some useful results out, even though there are systematic errors in models
Yeah.
or limitations.
Yeah, that's a great question. And actually, that's why I think like shifting from thinking about models just being good or bad, maybe in light of those systematic errors, we need to think about fitness for purpose, right? Because a model that has one systematic bias that doesn't have implications for your specific purpose can be a good model, right? And
Or could be
so,
useful models or something.
yeah,
Yeah.
useful model, yeah, or good for that specific purpose, right? It can still have utility. As far as I know, we have not unfortunately shifted towards like thinking in terms of where our models are fit or unfit. I'm part of CMIP trying to develop responsible use guidance that tries to look at the implications of those systematic errors to try and advise people about when a model might not be useful for their purposes. But we're still kind of just doing standard evaluation where we gauge for like empirical accuracy, right? Is there agreement with observation? Oh, there is. Great. That model is useful in a very generalized sense. So that's why I think we need this cultural shift, at least from my perspective. And I think, interestingly enough, the response to systematic biases is different across different modeling centers. I think we know that there's things like this SST bias that we need to clear up. But interestingly, the kind of going like train of thought about how to respond to those biases is default, let's just increase resolution and see if by resolving various sorts of processes they go away. So it's not a very sophisticated and targeted sort of intervention towards these biases either. And part of that, I think, is actually because of what model development looks like with CMIP and IPCC now, that, we have like 5 to 7 years between, model development cycles. And so there's not even really enough time in order to understand how the systematic biases have changed and have a targeted development approach that intentionally tries to resolve those, that is in any way collaborative across modeling centers. Sorry, if you can't tell, I'm mildly critical of model development culture and contemporary climate science.
Thanks.
Yeah.
I can just add one more quick. I don't have an answer. This is a very good question and something that comes up in ice sheet modeling quite a bit. I'll just offer one more thing and then I'll have to go in a couple of minutes. But on ISMIP 6, the ice sheet model intercomparison project for CMIP 6, we adopted this kind of perturbation approach, right? Where every model was asked to perform a control experiment where there's no future warming, and then an anomaly, an experiment where we supplied a ocean and atmospheric warming anomaly on top of a baseline. And then all of the results needed to be interpreted, appropriately. And there was quite a bit of criticism from the community that this sort of because a lot of models are initialized at a time when the ice sheets are rapidly changing, which is to say over the last several decades. By removing that control experiment, not only are you removing model drift, which you don't want, but you're also removing any modeled ice sheet change that you do want in there. So kind of like background change that is happening within the ice sheets, that's being removed, and so it's not part of your future anomaly forcing. And then it makes it very tricky to interpret you know, what that anomaly means as far as what the projection goes and how to add back in the background state. Anyway, and it also sort of I would say discouraged ice sheet modeling groups to ensure that their models reproduced the observed past in any way. So there were some model runs that where the historical, the Greenland ice sheet was growing over the last 20 years, and they were still weighted equally as a part of the ISMIP 6 ensemble. So that was where the criticism sort of originated from. All that to say that because of that, the ISMIP community is trying to move away from these sort of control and anomaly or perturbation experiments and move towards um, it, ha using observations as a metric to evaluate whether the models are reproducing the past and how trustworthy the future projections are.
Thank you all so much for coming, and thank you to Dennis and Monica for being our speakers and the interesting discussion. I had a great time. I hope everyone else did too. And I think we're going to move on to some team member updates to wrap up.
Yeah, this is just a chance as we close the meeting. If anyone has any announcements or relevant updates for the team, feel free to share those upcoming events, and maybe wave or something if you have one. And otherwise, we'll go ahead and close up for today. And yeah, you can access the recording and share it with your colleagues via our IARPIC website and the YouTube channel. So thanks very much. And I think that's it for the day. Thanks again, Monica and Dennis, for the great talk.
Thank you.
Thank you
Wonderful.
so
Thank you very
much.
much. Thanks. Bye-bye.